we have seen in our previous lectures that when fluid is coming from reservoir to wellbore to the surface, there are several pressure losses, and some pressures already we have calculated. For example, reservoir to wellbore, wellbore to the wellhead. Now we will try to see wellhead to the separator. There is one equipment called choke. So choke is an important part of your wellhead system or surface production systems, where you control the flow, how much pressure is there in wellbore, and same pressure you not deliver to your separator system. So in between there will be some restriction or choke. Okay, so choke when you are installing, so there will be certain relationship between wellbore to the reservoir to the wellbore to the surface. So how it is looking like this? Let's draw one figure. This is Q, this is P, and if I have initial reservoir pressure here, PR reservoir pressure, then after surface completion reservoir pressure will be down and it will be PWF. So flowing pressure when you have, so you have on IPR curve. Let's say this is one idealized IPR curve. We are assuming like it is curve actually, not linear, maybe two phase flow, and this is called IPR. We have seen. Okay, this is called absolute open flow. Open flow. So when there is no flowing pressure, so reservoir pressure is here and flowing pressure almost zero. So fluid flow will be very high rate. So that is called open flow. In the tubing, so you are reaching to PWH wellhead. When you are reaching wellhead, your curve will be like this almost. So this is surface wellhead and wellhead pressure is here, and your surface choke curve will be like this. This is surface choke performance, surface choke performance, and this is IPR, and this is del P2. Del P2 or loss in vertical tubing, loss in vertical tubing. And next is surface choke, and this is surface wellhead. This is wellhead. So flowing pressure, okay. So you can see because of huge pressure drop, you are getting less flow rate also, and your pressure is dropping, and surface choke performance also when pressure increasing, your flow rate also increasing. Now choke is required. I already told that because you do not give all the pressure to the separator, because you have to control the pressure, then you have to send to separator. If you are not controlling that one, then separation performance and other stories will be different, and your pumping performance also will change. So you cannot change suddenly all the parameter. For example, reservoir slowly depleting or pressure is going down slowly, and because of this slowly pressure degradation in the reservoir, you cannot change your pumping performance or choke performance, your wellhead performance, your separator performance. So you have to get stable production for longer period of time. For that you have to install a choke. So normally choke will be two type, one will be variable choke, one will be fixed choke. And how the pressure is changing from reservoir to the surface, we can draw one figure again. This is pressure versus flow rate diagram. This is pressure versus flow rate. Flow rate, this figure. Okay, and this figure it will show depth versus pressure, how pressure is changing. So initially let's say wellhead pressure is here, PWH wellhead pressure, and this is depth, this is pressure, this is flow rate. Okay. And pressure P, actually we are writing every time P, so it should be noted that pressure is P. Now if you have pressure here, this is del P, one pressure drop here, and this flowing pressure will go like this, Okay, this is flowing pressure traversal, flowing pressure traversal. Okay, so from if you are increasing depth from surface to wellbore, so you can see how this pressure is changing. So initially pressure is very high at this point A, then slowly pressure is going down and it is reaching to B or at wellhead. And because of there are several restrictions in the reservoir, sand phase completion, there will be some restriction in the reservoir, some restriction, piping restriction, wellhead, lots of connection mechanisms will be there, there will be some restriction, choke restriction, then you are reaching to your surface separator system, again surface separator system, again there will be several pressure drop, then finally you are reaching to your stock tank barrel. And this whole system will be driven by your reservoir pressure only. Actually, if you are giving extra pressure using artificial lift or other mechanism, so that means you are giving some extra energy. That means your energy extra means coming from electricity, or you are burning somewhere fuel, and that will cost money. So if you want to reduce that one, the reservoir pressure you use and you design the whole system and operate in synchronized way. You cannot change choke parameter or other parameters suddenly, because you need stable production for longer duration time. That will be more economical. And if you are getting today, let's say, very high production, tomorrow because of sand injection or gas coning or water coning, your production got down, or maybe artificial lifting system failure, or maybe surface production system not working, that will be costing huge. So your actual benefit will be lower. So your main target should be stable production for longer period of time. Now let's draw one choke. So normally people will be drawing choke like this: restriction, this is diameter of pipe, it will be like this, wellhead, then there will be pipe, okay, this reservoir and tubing. Okay, I'll draw this whole thing actually. So this is sand phase, this is cementing, this is wellhead, and there will be choke. So choke will be drawn like this. Okay, so because you are creating restriction, choke means restriction, your piping diameter will be reduced. So initially let's say diameter is D, and this diameter become D1, and this is inlet or upstream, this is outlet, or downstream, down. So sometime we specify it is downstream pressure or upstream pressure. Okay, now at inlet pressure P1, diameter, okay, they are saying this is D1 diameter, okay, this is D2 diameter. The inlet pressure P1, flow rate Q, and so outlet flow rate, if diameter is same, then flow rate will be same, because if mass, we are assuming if density is constant, then for mass balancing your flow rate will be same. If density is changing, then flow rate may be different. Okay, so then now we need to understand how this fluid will be flowing through the choke. So we need to know pressure at P2. Okay, so we have to know pressure P2 divided by P1, because wellbore pressure fixed, wellhead pressure fixed, so that wellbore whatever delivering, that upstream pressure may be 1000 bar or 100 bar. Okay, now downstream pressure actually you can control. Let's say you can put very big restriction after choke, right? This is choke, okay, CHOK. So after choke, you can control the pressure, but upstream control pressure you are not controlling, because it is controlled by your reservoir system. Now let's say initially reservoir downstream pressure it becomes 0. Okay, very low pressure P2. When P2 is very low and P1 is very high, so that time you will get very high flow rate. Okay, so you got first point. Now you create certain restriction, so you gradually increase P2 value. When you are increasing P2 value, what is happening? Your flow rate will be little bit lower. Again you will little bit reduce P2 value, P2 value reduce, P2 value reduce. So flow rates gradually to be lower. So after certain time, if you still your flow rate will not change. Okay, this is flow rate actually. Okay, so take specific P1 value or upstream or wellhead pressure value, and downstream pressure you are trying to control. When downstream pressure initially 0, flow rate will be very high, then downstream pressure gradually increasing. When it will increase up to certain value, your flow rate will not change. Okay, so that point where flow rate becoming almost constant is called critical flow rate, critical value. Okay, so this area is critical area. Okay, and this is subcritical area. Okay, so this pressure ratio is called critical pressure ratio. Okay, now once let's say you have one choke, it is running under critical condition. If you change P2 pressure, your flow rate will not change actually. So your reservoir and whole restriction will have same resistance, same flow rate will be maintained, but down after choke, whatever pressure you are trying to play with, for example your separator system changing or anything you are doing, so upstream will not get affected, because if upstream or wellhead and wellbore and reservoir it is getting affected, so there can be multiple problem. One can be gas coning, water coning, more sand can come, debris can come, or some blockage will be there, artificial lifting system can fail, or some valve can fail, wellhead, so there will be multiple issues. And if you are working for wellbore condition, let's say reservoir, sand phase completion, sand control system, artificial lifting system, that will be expensive process. In many cases wellbore will be inaccessible areas. For example, it may be in the ocean, or it may be in a forest, or in a desert area where road may not be there, where accessibility will be very difficult. So in that case, helicopter carrying all the equipment and removing piping, tubing, then recompleting the wellbore, it will be very much expensive affair. So instead of changing wellbore or the tubing pressure and flow rate, you change downstream of choke pressure pressure, so that your whole system will be synchronized, and after choke you can change your pressure. So that will be much more easier to handle, because something is on surface, handling is easier, because in machinery you don't have to bring a rig for drilling or redrilling or completing. Okay, so that's the beauty of the choke in system. Now critical pressure, how to calculate it? Let's see this formula. So again let's draw the choke. Right, so if you have outlet pressure divided by upstream pressure, outlet pressure divided by upstream pressure, 2 by k plus 1 k divided by k minus 1, this power. If this ratio becomes 0.528, if this ratio becomes 0.55, then you can say this is a critical pressure. So that pressure is critical pressure, right? So this pressure is critical pressure, P2 by P1 or P outlet by P up, that ratio is called critical pressure, and K value is taken as 1.28 for natural gas. But if you are not taking K value 1.28, that K value that critical pressure ratio will be different. So in that case you have to calculate this, use this equation again, you have to calculate, and you have to check point where it is coming 0.55 or different. Based on that you have to design your choke. And this K value depends on your component of the fluid. K means specific heat ratio, Cp by Cv. Cp by Cv equals K. Now single phase liquid flow, if choke is having single phase liquid flow, the formula is that Q equals Cd into A 2Gc del P by rho, and the parameters are Q is a flow rate and unit is cubic feet per second, and if you are using barrel or other terminology, then you will get some constant also. Cd is a coefficient of discharge. So this value will be given, or you can calculate. So normally I give value 0.62, and if it is not given you can assume, or if it is given then you have to take as it is. A means choke area. Area of choke, it is feet square, and GC value is equal to 32.17 lbm pound mass divided by lbf second minus 2, and del P is the pressure drop, is unit is lbf per feet square, and rho is the density, fluid density lbm ft cube. And all this formula is taken from book Go et al. If something goes wrong, please follow the book. And if you are taking US field unit, then formula little bit modified because there is some constant term will come. Okay. So in that case, Q is flow rate, D2 is choke diameter. This is choke diameter. So you have seen this one we specified as D2. This is D1, choke dia, and del P value already till the PSI. Okay. Okay, you are using field unit, so it is PSI, and rho will be a density parameter. Now single phase gas flow. Now single phase gas flow, when you are considering, then there are two parameters will be there. One will be subsonic flow parameter, another will be sonic flow parameter. Let us first assume subsonic flow. Subsonic flow formula is that, this is again Guo book, Guo et al. Okay. So the QAC gas flow rate MSCF per day, and P up is the upstream pressure in choke, that is PSIA, and A2 is the area, cross section area of the choke. This is feet, this is inch square, they are taken inch, and K already specific heat ratio, gamma G is specific gravity of gas, is specific gravity of gas, T up upstream pressure, the temperature unit is degree Rankine. So you should remember this is degree Rankine, 460 plus Fahrenheit, and P downstream pressure PSIA, upstream pressure PSIA, K value already given 1.28. Okay. Now Reynolds number for determining CD, you have to use this formula, where QSC already MSCF per D, that flow rate of gas, gamma G already told, specific gravity gas, air 1, and mu is the viscosity term, Cp, and D to the choke area, choke diameter. Now gas velocity subsonic flow is less than the sound velocity, so V will be upstream velocity, V square upstream velocity, and Cp specific heat, specific heat 1.187.7 lbf feet lbm R for air, specific heat gas constant, and other parameters almost known. GC value is at 32.12. Okay. Now we will go to sonic flow. In sonic gas flow, again we have to use the formula. The terms are CD, the coefficient of discharge, area of the choke, upstream pressure, K value already known, T upstream temperature is given. Okay. So if we approximate, the value comes like this, velocity. Okay. Next is temperature at choke. When gas is at very high pressure and you are reducing pressure, that means gas will be expanding. When it is expanding, if you know PV equals nRT formula, so using that formula actually you can see the temperature will go down. So how much temperature will go down, you have to calculate. If you calculate the temperature, then actually whether you can actually there will be any frost formation after choke or not, you can calculate. So downstream pressure equals T upstream pressure, Z outlet means this is compensative factor. Okay, ability LIT factor. Okay, and K value already you know 1.28. Okay, so using that we will try to solve one problem, all this formula. So this problem is given in the GUO book. A 0.6 specific gravity gas flows from a 2-inch pipe. So first draw the 2-inch pipe. Okay, this is 2-inch diameter. 1-inch orifice type choke. So that means I have restriction, and this is 1 inch. 1 inch. Okay, so D1, D2. Okay, the upstream pressure and temperature. Upstream pressure is given P equals 800. Temperature is given 75 degree Fahrenheit PSI. I should write unit also. The downstream pressure 200 PSI, measured 2 feet from the choke or orifice. So from 2 feet, this is 2 feet actually. So far away from the choke restriction. The gas specific heat is given, heat ratio. So K is given 1.3. CD value you can calculate, or here in this problem I have given 0.62, and viscosity of gas, okay, it is taken as 0.0125. So using this data actually you have to calculate expected daily flow rate. Does the heating needed or not, because temperature will be go down because of gas expansion. If temperature goes below 0 degree centigrade, then you have to put some heating coil so that the choke will not get blocked by ice, frozen ice. What is the expected pressure of the orifice outlet? So orifice outlet pressure also you have to calculate. Okay. So first you calculate this one, P outlet by P up, that's sonic condition you check. So here value is given like 2 by 1.3 plus 1 K minus 1, or 1.3 actually, 1.3. So because K value is given 1.3, so it is becoming 0.546. Okay, now P down by P up, P down by P up equals 200 is given 200. You can see somewhere here P down is given 200 and P up upstream is given 800. So it is becoming 0.25. So you can see this 0.546 and 0.25. 0.546 is higher. So it is a sonic condition. So you have to use sonic equation. Okay. D2 by D1. D2 by D1 diameter ratio will be 1 by 2 because 0.5 the ratio, so there will be no unit. And CD we are assuming CD equals 0.62. I have given in this problem, but if it is not given you can assume 0.62 or around. It may be differing also, but approximate thumb rule is that if you use 0.6 or 0.62 that will be okay. So now QSC. So QSC flow rate, first question is the expected daily flow rate. QSC equals 879. So 879, CD value 0.62, A value is pi r square by 4. Pi r square means 1 inch. 1 inch divided by 4 means pi by 4 into 1 square. Okay, and P upstream pressure is 800. Then root over coming K value 1.3, gamma G value 0.6. 0.6, and T value is coming 460 plus temperature given 75. Uh, 2 by 1.3 plus 1. Oh, gamma G value is given, actually I wrote wrongly, 0.6 it is given, specific gravitative gas is written there. And 2 by 1.3 okay. Then this whole parameter we have k plus 1, 1.3 plus 1 divided by 1.3 minus 1. So finally it is coming 12,743 MSCF per day. Okay, this is one solution. Next is, does heating needed? So for heating needed, you have to calculate T upstream, T downstream temperature. So T downstream, so T upstream temperature, Z upstream divided by Z outlet divided by P outlet divided by P up, K minus 1 by K. So this value if I put, it is coming 465 degree Rankine temperature, means 5 degree Fahrenheit less than 32 degree Fahrenheit. So 32 degrees Fahrenheit is that frozen ice will be formed, or water will be frozen, it will form ice. So it is becoming less than the freezing point. So that means ice formation will be there. So heating is required. So you have to put heating coil around the choke so that there will be no ice formation all around, and choke will not get blocked. Okay, so then heating is needed. Heating is needed. Okay, now outlet pressure, P outlet. So what will be the P outlet pressure? P up by P outlet divided by P up equals, if we put values 800, 0.546, so it is becoming 437 psia. Okay, this is the another answer. Pump is used everywhere, and we are alive because one pump is working. The pump works sometime for 60 years, 70 years, 100 years, 120 years. If you read the book Ikigai, you can see people in Japan, Okinawa island, they are living more than 100 years. So their pump, one pump is there here, left side of your chest, that is heart. Okay, that is pumping, that's why you are alive, and that runs sometime in India about 70 to 80 years average, and in Japan it will be a little bit more. Japan, Korea, their life expectancy more, so their pump is working more. But as scientists or engineers, we are unable to develop such pump which will be running for longer time. People are trying to replace heart by artificial mechanism. For example, centrifugal pump or other type of pump, they are trying to replace, so that your life will be more longer. If they have any heart blockage or you have any heart ailment issue, so they can replace your heart by your centrifugal pump or other type of pumps. So pump is very important. You are getting water in your flat buildings because pump is running there. And your machinery, like fluid machinery also, for example ice engine, there is one pump actually. If you see other type of machinery where fluid flow is happening, so some majority of the time one pump is required. So pump is an independent part of our modern life actually. Although you go to add AI, ChatGPT, everything, but the something is basic you cannot remove. For example, your heart you cannot remove with AI, ChatGPT. So you can see this hand pump I have taken from internet, so without any source. So this is also one pump actually, And there are several types of pumps. One will be like hand pump, you have seen. One will be cycle syringe pump, like roadside cycle shops, they will have cycle pumper. So you move up and down on handle, and slowly your tube will be filled with air. So at up to certain pressure, you just continuous pumping. So there is pump actually, right? Another pump can be like your heart also pumping blood in your body. This pump is giving water to your village households. And some other pumps such as blower, that also can be a pump actually. Your ceiling fan, or maybe rotating over your head, there is also one type of pump. Okay, and there are different types. For example, one will be axial type pump, or a reciprocating type pump, or a centrifugal type pump. So let's see what are the different types of pumps available, and how can you use for your day-to-day life to your artificial lifting system or surface production operation systems. Okay. So, so a pump use in your human heart system, and your cycle pumper in your household application, agriculture application, or surface production operations. Surface production operations, how surface production operation requiring pump? Except if you have lower pressure in your surface systems, and somewhere you need to increase pressure, or you need to pump the fluid to your tanker, or you have to raise the level of fluid. So in that case you use pump. Artificial lifting system, already it is actually pump, but we in oil industry we use the term artificial lift, because artificial lifting fluid from wellbore to the surface. So there are ample application, heavy application is there. And the pump can be very small, like injection needle. You got all COVID shot, right? So injection needle, that is also actually pump. You are pumping small amount of fluid to your body. And big amount of pump, for example, you have a flood, and your municipality wants to clear water from your housing area. So immediately they will be putting big pumps, and they will be removing all water out from that specific area. So that is also pump. So there are small minute pump like heart valve, they are replacing, trying LVAD, left ventricular assistive device. They are trying to replace your heart mechanism using your mechanical valve. That is also small pump they are using there. Your big pump is for your industrial applications. So there are several applications, wide applications are there.